Hello, my name is Mike Flack, and today I'll be talking to you all about symbolic analysis and code emulation. So, two of the main methods that we should all be familiar with for binary analysis are static analysis and dynamic analysis. So, typically, static analysis, you're statically gathering indicators from a sample without running it. So, you'd be using things like CFF Explorer to maybe look at the like NT headers, imports, exports, or resources from a binary. And of course, with dynamic analysis, with that you're gathering indicators during runtime of a sample. So you could be looking at things like network traffic, or if there were any artifacts created by the sample, like things dropped into temp folders, or maybe changes to registry keys, things like that. Both really good indicators, to keep an eye on because you might want to use them to create YAR rules or whichever, for further identification or attribution. But there's actually a couple more than those two. What we'll be talking about later on specifically are symbolic data analysis, SDA, and concolic data analysis, CDA. And then we'll have a slide or two on code library emulation. So, of course, just referring back, static analysis, you have two examples here, CFF Explorer and Cutter, which is just the graphical version of Radar. So, of course, just looking at some either NT header information or here things like when the file was created, modified, accessed, any file info that we can view, like maybe about how it was compiled, if it hasn't been scraped. And then dynamic analysis examples. Here we have x32 debug. You might use WinDebug Preview, or if you're on Linux, you'd be using something like GDB. And then here, another example of dynamic analysis, you might want to look for calls made by the executable. So you'd be looking at if it was making calls to things like shell execute, or allocating memory, or writing to that memory, anything like that. And this one's actually pretty helpful because you can limit it to specific libraries that you're interested in, like maybe specific Windows libraries, or maybe .NET ones if that's the kind of binary that you're analyzing. So, of course, what is symbolic execution? Symbolic execution is a way of systematically exploring as many execution paths at the same time without requiring concrete inputs while doing so, which is what dynamic analysis would require. We can get into why that is in a bit. But rather than taking on fully specified input values, the technique abstractly represents them as symbols, resorting to constraint solvers to construct actual instances that would cause property violations or solutions. So the pros: there is no division by zero, no pointers ever dereferenced, there's no backdoors that can bypass authentication, or things like blindly debugging and then detonating the sample and causing who knows how many issues. And then of course the cons: no automated way to determine jump table results, and we can also get into why that is in a couple of slides. So for example, on the left you have what might be like a decomp or source code, and on the right you might be looking at that and thinking, what is that garbage? That's actually the representation of a control flow graph when you're trying to represent the solving constraints for each block within it. And it might be confusing to look at it in that form, but the next slide might be something you're more familiar with. And this is a control flow graph generated by Radar, and it just shows the disassembly for each block, and then true or false if the condition's met, and how it flows into the next graph, and then so on. So What constraint solving does is it sees these blocks and then it attempts to recognize what the constraints are to solve it. So like with the first block, it has a jump if equal to, and then some address, which is the block to the right. And then, so essentially constraint solving would see that and say, essentially like solve for x, depending on what values of x, where do we go in the graph? And that's essentially what constraint solving is. And symbolic analysis is just going through all of those different constraints and solving for them to determine what inputs get us where. So symbolic and concurrent analysis, essentially the provided sample is disassembled, and then static analysis performs symbolic or concretely. Symbolic analysis, symbolic execution reverses the code considering symbolic input value or variables in place of concrete static values. So you have a complete exploration of the control flow graph and all its paths. In concolic or concrete symbolic analysis, the execution trace of the disassembled code is guided by provided contextual information and therefore has similar drawbacks to dynamic analysis. Meaning the exploration is limited within the CFG by the provided context or input. So how might we use symbolic analysis? So for this, you would probably use the Anger Python library, which is a multi-architecture binary analysis toolkit with capability to perform dynamic symbolic execution, which is just another term for symbolic analysis, or various static analyses on the binaries. Before Anger, you might have heard about PE-file or Life, and those are other Python libraries you can use to do static analysis on binaries. PE-file, that one is strictly Windows PE files, of course. Life, that one can do Windows PE. It can do Linux ELF, and then it can also do Mach-O for Mac. I want to say it might even be able to do APKs, but can't guarantee that. Anger is more powerful, though, because we can symbolically solve constraints within the binaries given limited complexity. So we're not just doing things like looking for min-max hex ranges of the binary. We're also using it to, go through those CFGs and solve the constraints to determine what inputs we need to reach them. One example, though, where we're going outside the bounds of what it's capable of, outside the scope, it would be single block high recursion samples. And the reason why they would fail is because since constraint solving requires that it traverses each block, it provides the constraints for them, and then attempts to solve for them as it goes down that control flow graph. If you have something that's a single block high recursion, where it's just repeatedly recursing through itself or another block, you're going to hit memory limits for what Anger is able to model and then solve for. So that's something you have to keep in mind when you do it. So here we're just going to show how the Anger is able to load the binaries and represent them. Anger uses something called CleLoader, which is actually another dependency or library within Python that it uses. But it just uses it to represent those binaries into a virtual address space. So you can see at first it starts off as a project.loader. That's with the binary and any shared objects loaded into it. You can see then, of course, in the next part where it goes on to show the shared objects. Those are just two Linux ELF libraries that are linked to the main object or binary. And then the next part, we show the min, max hex ranges for those objects. And then the main object, which is the main binary that those two shared objects are linked to. And then we can also see the min, max hex ranges for it, which is 0x4000 and 0x60721F. And then referring back to what we said earlier, some of the static analysis functions you can do with it. So you can query the objects to determine, do they have things like an executable stack, and are they position independent code. So that's some of what you can do in terms of static analysis using Anger and CleLoader. So of course, how does it actually manage this? The constraint solving portion. So Anger uses a solver engine, so that when a binary is loaded and the project object is provided, we not only have the symbolic states of each function, but also the symbolic values. Rather than being limited to concrete static values, say like if we did dynamic execution where we provided input at the beginning of that program, and that's a hard concrete value, and then we get whatever output that comes from it. Instead of doing that, we're providing symbolic values or names or placeholders, and then solving for it as an arithmetic problem given provided abstract syntax tree. So an example of what that constraint solving might look like. So registers and memory spaces are treated the same way, and it allows us to enumerate the different paths given the provided constraints and their possible solutions. So an example of that is we have the state solver here, and we've added a constraint that x is greater than y is greater than 2, and x is less than 10. So if we evaluate or solve for x, what is it? And in this case, it's 4. And if that still doesn't make sense in traditional generic programming terms, you could say foo is greater than bar is greater than 2, and foo is less than 10. So what is foo? Foo is 4. So potential applications for symbolic analysis. It's not limited to these, but these are some of the more common instances of what it's used for. You have code audits, exploitation development, and fuzzing, which in this case, kind of go hand in hand. Binary capture the flags. So if you are given a binary and you have to retrieve a flag for it, or figure out what the input is to get the flag, this is something you could use it for, because it will, of course, it'll traverse that CFG, provide the constraints for it, and then it'll solve for it until it generates whatever that key is to get the flag. And then another application is malware analysis. If you want to continue learning about Anger and symbolic analysis, you can go to this GitHub repository by Jake Springer. It's Anger CTF. They provide a bunch of tutorials and examples of what Anger is and how to use it. So lastly, code library emulation. I'm just going to go through this real quick because we're slightly over the time limit. So instead of statically inspecting a sample using somewhat complicated symbolic analysis or even dynamic analysis that requires detonating a sample, you can use libemu emulation library. Libemu makes it possible to emulate API functions from a program without risking infection. It can even be done with Windows shellcode on Linux. So what it does is it just disassembles binary, looks for function calls or API calls, takes the arguments for those calls, and then attempts to emulate the output. So it does it all without actually running it and executing that program. So it used to be, originally it was git.carnivore.it libemu, but that's deprecated, abandoned, and it's since been adopted and reworked by David Zimmer as scdbug.exe. And there's the GitHub link you can get it from. It's also already included with FlareVM as a debugger. So here's an example, just real quick, of using scdebug. And this particular example, it's an older one that I used. It was a shellcode that I wrote, and you can see the calls that the shellcode is making. So load library for the URL mon DLL, and then the URL download to file call from URL mon.dll to go out to the GitHub, pull that link, save it as notmalware.test, and then you have the win execute for that shellcode, sleeping, waiting for the file or the malware to execute, deleting it to cover its traces, and then exiting. So, and this is just a real quick example of what you can do. And that link is still real, if still active, if you want to go to it and see for yourself. But yeah, real quick. So, I mean, that was symbolic analysis, and real quick, an example of code emulation. Hope it was interesting, and thank you for your time.